In the previous lecture, we looked at how to represent a system of linear equations using matrices and column vectors. What's left for us to do now is to translate our three operations that we used in order to transform our linear system into a way of transforming our matrices so that we can find our solution to the linear system. So if you remember, we had three operations that we could perform on equations in a system of linear equations, which gave us an equivalent system that made it easier to see the solution. The equivalent row operations seem almost exactly the same. So instead of swapping two equations, we can swap the location of two rows. And instead of multiplying each entry in a single equation, we can multiply each entry in a single row by a non-zero quantity. And finally, our third operation becomes multiply each entry of one row by some quantity and add these values to the entries of the same columns of the second row. Leave the first row the same, but replace the second with the new values. We have some shorthand that we use to explain as we go along what it is that we're doing to our matrix. So our swap notation, we use a little double-sided arrow to show I'm swapping rows I and row j. I will write whatever multiple I'm multiplying row I by to show that that's what I've done, and alpha row I plus row j says I'm going to replace row j with this linear combination over here. So we are now going to call two matrices A and B row equivalent if one can be obtained from the other by a sequence of row operations. So we're being very careful here to say row equivalent, and it doesn't mean in any way that the matrices are the same, it just means that you can get from one to the other using a sequence of row operations. So for example, we claim that this matrix A is row equivalent to B. Well, let's think about how we could have got from A, which is over here, with row operations to B. Well, you'll notice that the first thing that we did was we've swapped row 1 and row 3. So I've got a 1, 1, 1, 0, 6, which was row 3 and now is row 1. I haven't done anything to row 2, and I've put row 1 into the new row 3 spot. So if we have a look at matrix B, we've now got row 3 and row 2, but how did we get row 2? Well, we can get row 2 by subtracting twice row 1. So if we say row 2 minus twice row 1, then we get, so we're not changing row 1, we're not changing row 3, but we're saying 5 minus 2, which is 3, 2 minus 2, which is 0, minus 2 minus 0, which is minus 2, and 3 minus 12, which is minus 9. And that's how we got to our matrix B. Of course, our little intermediate matrix over here is also row equivalent to both A and B, and you could find many more matrices, and any pair of them would be row equivalent. Why is this important? Well, row equivalent matrices represent equivalent systems. So this is a theorem. Again, you can have a look at the proof if you want to. But the basic idea is that if we have a system of linear equations which we want to solve, but is in a kind of complicated form, we're going to put it into augmented matrix form. We're going to do our elementary row operations to transform it into a form that looks roughly like this, so lots of zeros and ones. And then when we transform that matrix back into a system of equations, hopefully we'll end up with something that looks like a system of equations that's easy to read off the solutions. It's not always going to be possible to make it look exactly like this or read off solutions like so, but we'll get close to it and it'll help. So let's use our row operations to solve the system of equations we have already seen and solved using equation operations. So I've gone ahead and I've found the augmented matrix for this system of linear equations, and now we're going to see if we can transform it into something that makes it easy to read off the solutions. So if you remember, when we were solving the system using the equations, the first thing we did was we did an equation operation to eliminate the x1 in the second equation. And what we actually did was we subtracted off the first equation from the second equation. And in terms of the matrices, that's exactly what we're going to do. So we're going to say row 2 minus row 1. So a good habit to get into when you're working with matrices like this is to write down the things that you aren't going to change before you do anything. So we're only changing the middle row, so I'm going to write down my top row so that it doesn't get changed by mistake, and I'm going to write down my third row so it also doesn't get changed. Okay, so now I need to say row 2 minus row 1. So that's going to be a 1 minus 1 is a 0, 3 minus 2 is 1, 3 minus 2 is 1, and 5 minus 4 is 1. Okay, great. So the next thing that we did when we were working with our equations was we wanted to eliminate the 2x1 term from the third equation. And if you have a look at what we've got in our augmented matrix now, we can't use the second row because it's 0, so we must use the first row. So what we're going to do is we're going to say row 3 minus 2 times row 1. So again, write down the things that aren't going to change. And now we work with our third row and first row. So it's going to be 2 minus 2, which is 0, 6 minus 4, which is 2, 5 minus 4, which is 1, and 6 minus 8, which is minus 2. Okay, what next? Well, the next thing that we wanted to do was eliminate the 2x2 term which appeared in the third equation. And in order to do that, well, if we used row 1, then whatever multiple of row 1 we added to row 2, to row 3, we'd end up getting a term involving a 1 coming back and spoiling our lovely 0. So let's not do that. Instead, we're going to use row 2, and we're going to say row 3 minus 2 row 2. So again, write down stuff that isn't going to change. Which is our first 2 rows. And now we've got 0 minus 0. Got 2 minus 2. And we've got 1 minus 2, which is a minus 1. And minus 2 minus 2, which is minus 4. So the last little thing that we can do is convert this minus 1 into a plus 1 by multiplying the third row by minus 1. So the final little thing we're going to do in this example is say minus row 3. So row 1 doesn't change, row 2 doesn't change, and row 3 gets multiplied by minus 1, so we end up with that. So what have we actually done? Well, now we can take this augmented matrix and write the equivalent system of linear equations. So this goes to the set of linear equations 1 times x1 plus 2 times x2 plus 2 times x3 is equal to 4. 0 times x1 plus 1 times x2 plus 1 times x3 is equal to 1. 0 times x1 plus 0 times x2 plus 1 times x3 is equal to 4. So that's what we found, but we've done it a bit quicker. And now we can read off our solutions because we can see from this third equation that we've got that we must have that x3 is equal to 4. And then when you plug that into our second equation, we get that x2 plus x3 is equal to 1. So we must have x2 is equal to 1 minus 4, which is minus 3. And then we can play the same game and you could work out what x1 is equal to. So that would be x1, we've got 2x2, which is going to be minus 6, plus 2x3 plus 8, so that's plus 2. So we've got x1 is equal to 2, which is the solution we found previously. Now, one thing you might be thinking about is it would have been really nice if we'd had rows 1 and 2 looking similar to row 3, in that if we just had, for example, x1 without any terms involving the other variables, we could have just read off that answer. And likewise, in our second equation, if we just had a term involving x2 but not x3 or x1, we could have just read out the answer. And if you were thinking that, that's exactly what we're going to do. So we're going to add a little bit to our technique so that ideally we are able to just read off the solutions without having to substitute back in like we did to find x2 and x1. So that brings us to the idea of reduced row echelon form of a matrix. I'm going to explain why we call it reduced row echelon form once we've seen what it actually looks like. So we say that a matrix is in reduced row echelon form if it meets all of the following conditions. Firstly, if there's a row where every entry is 0, then this row lies below any other row that contains a non-zero entry. So basically we want to swap any 0 rows with lower down things so that we only have 0 rows at the bottom of our matrix. Now we look at the form that we're going to have for any row that isn't non-zero. The leftmost non-zero entry of a row is equal to 1. So that corresponds to what we did here, where we worked our leftmost entry in any row was a 1. So we do row operations until we get there. The next bit is the leftmost non-zero entry of a row is the only non-zero in its column. So that's new. Okay, we haven't done that yet. We'll see how we work it. If we go back to what we worked on here, the leftmost, we're ideally wanting to turn things above this into 0 as well. And finally, if we consider any two different leftmost non-zero entries, one located in row I, one in column J, one in row I column J and the other in row S column T, if our row number is bigger than our I, then it must be that our column is bigger than our previous column. What that is really just saying is we want to have the ones going diagonally down like this. We don't want to have a 1, for example, over there, or over there, or over there. These sound like very abstract things, and I wouldn't really worry too much. Once we start seeing how we work with the matrices, you'll get an idea of the picture that we want. We also have some terminology. A row of only 0 entries we call a 0 row, unsurprisingly. And the leftmost non-zero entry of a non-zero row we call a leading 1, which kind of makes sense if you look at our previous example over here. It's like these ones are coming in and leading the row. A column containing a leading 1 will be called a pivot column. And the number of non-zero rows will be denoted by R, and it's also equal to the number of leading 1s and the number of pivot columns. Don't get too hung up on this. The technique that we want is going to become pretty straightforward. You can also have a read for this, but it's not super important. So just to have a look at what we mean, here we have an augmented matrix C, and I claim that it is in row echelon form. So let's go back and check what our criteria are. If we have a non-zero row, it has to be below any non-zero rows. Well, we've got that. Okay, because both our 0 rows are below the rows that have non-zero entries. Next, we have the leftmost non-zero entry of a row is equal to 1. So let's check. If we look at row 1, the leftmost entry is equal to 1. We look at row 2, yes, its leftmost non-zero entry is 1. Same for row 2, and row 3 and 4 are all zeros. Okay, so we've got criteria 2 sorted. The leftmost non-zero entry of a row is the only non-zero entry in its column. Okay, the leftmost entry of a row is the only non-zero thing in its column. Yep, that works for that one. Let's have a look. This one, yes, there are zeros everywhere else. This one, yes, there are zeros everywhere else. And for these columns, we don't really care what's going on with them because they're not the leftmost entry. Okay, so we've got that sorted. And if we consider any 2 different leftmost non-zero entries, one located in row I, column J, and the other located in S and T, if S is bigger than I, then T is bigger than J. And all that's saying is that we arrange the rows so that the most leftmost, slightly less leftmost, and so on, so that we get this kind of form here. So it's helpful to have a look at a matrix that isn't in row echelon form. So the first thing you'll notice with matrix E is we've got a 0 row here, which should in fact be moved down to the bottom, because we've said that we want all our 0 rows at the bottom. The leftmost non-zero entry of a row is equal to 1. Well, we have a bit of a problem going on here with row 2 because the leftmost entry is a 5, which is not okay. We have the leftmost non-zero entry is the only non-zero in its column. Well, let's have a look. Over here we have a leftmost 1, and this 7 should have been converted into a 0, so that we only had zeros and 1 in that column. So it fails on that count. And then finally we have what is going to be kind of the echelon condition. We have a situation where we have a row here which has a 1 which is further left than one of the higher rows. So it's kind of out of place. So our matrix C was in row echelon form, but our matrix E was not. So we have a couple of theorems that are useful for our row equivalent matrix in echelon form, and they're relevant because we're trying to find solutions to systems of linear equations. So the first thing that you might think about is, well, can we always find a matrix in echelon form given some augmented matrix? And this theorem says yes. Suppose A is a matrix, then we can always find another matrix B where A and B are row equivalent, so they represent equivalent systems, and B is in reduced row echelon form. So you can always put a matrix into row echelon form. The next thing you might wonder is, well, what if does it depend on which order you do stuff? What if you get 2 different reduced row echelon forms? Then maybe you're going to get different solutions. This second theorem here says that's not the case. If you have an m by n matrix A and B and C are m by n matrices that are row equivalent to A, and they're in reduced row echelon form, then you will definitely have that these two matrices are the same. They're not just equivalent, they're identical. So this is saying if you do your work correctly, transforming A into reduced row echelon form, then you will always end up with exactly the same matrix. There aren't two that could work. So now we're actually in a position where I can explain where this name reduced row echelon form comes from. So the word echelon was initially used in the military, and it describes a formation of troops, ships, aircraft, or vehicles in parallel rows with the end of each row projecting further than the one in front. So you have a situation, for example, with troops, where you have parallel rows where your first row is slightly ahead of your second, is slightly ahead of your third, is slightly ahead of your fourth. Or likewise with ships. And over here is a picture of some loghead fighter planes, also in echelon form. So as we saw, when a matrix is in echelon form, you have rows, you have the upper rows leading with their leading ones ahead of the lower rows. So that's where the idea of calling it echelon form comes from. And row, just to make it clear that we're working the echelon pattern with our rows. The reduced comes from the previous two theorems we looked at, which said you can always turn a matrix into reduced row echelon form, and that's unique. So what we're meaning by reduced, we have kind of taken it down to the smallest matrix that it could be, or the simplest matrix. It has been fully reduced. Can't do any more. So that's why we call a matrix a reduced row echelon form. Okay, so that was quite a lot of theory. Now let's just practice using this technique. Now it's not mentioned in the textbook, but this technique of taking an augmented matrix and turning it into reduced row echelon form is often called Gauss reduction or Gaussian elimination. So here we go. So the first thing that we're always going to want to have is that our top left, if at all possible, is a 0, is a 1. And there are three things we can do. We can take a multiple of the row, so we could divide through by -7 and that would give us a 1. Or we could add or subtract some multiple of a different row. So for example, we could add 8 times row 3 to row 1. But the simplest is always to have a quick check and see if you haven't got a row that already has the 1 in the place that you want, and then swap them. So we notice that row 3 actually has a 1 when we want, so let's just keep life simple and switch row 1 and row 3. Because if you're anything like me, it's very easy to make mistakes when you're doing basic arithmetic. So less of that is great. So there's my third row that's now become my new first row. I haven't changed my second row, and my third row is what was my first row. Okay. So the reason you want this 1 here is because then you can use multiples of this row to get zeros in the second and third row beneath it. So let's go ahead and do that. We're going to say, so I want to get this 5 to be a 0. So here we go. I'm saying row 2 minus 5 row 1. Now, writing down a row that is not changing. Bottom row is not changing. And here we've got 5 minus 5 is 0. 5 minus 0 is 5. We've got 7 minus 20, which is minus 13. And we've got 24 minus 25, which is minus 1. And now we're going to play the same trick to get this minus 7 to be a 0. We're going to add 7 times row 1. So we're going to say row 3 plus 7 times row 1. Not changing the first row, not changing the second row. And here we go. Minus 7 plus 7 is 0. Minus 6 plus 0 is minus 6. Minus 12 plus 28 is 16. And minus 33 plus 35 is 2. Okay. So now we want to work on getting this 5 to be a 1, because we want the leftmost non-zero entry in this row to be a 1. And the simplest thing here is just to divide through by 5. So we're going to take 1/5 of row 2. So we write down our first row and our second row, our third row, which aren't changing. And now we divide this row by 5. So that's 0, 1, minus 13 over 5, minus 1 over 5. And now that we've got this one over here, we want to make sure that it's the only non-zero entry in this column, which means we need to get this minus 6 to be a 0. So the only thing we can do really is add 6 times row 2 to row 3. So again, be careful when you write down the rows that are not changing. So our 0 doesn't change. Now we've got a 6, a minus 6 plus 6, which is 0, and we've got a 16 minus 13 over 5 times 6, and if you work that out, you will find you get 2/5, and if you say 2 minus 6 over 5, you should get 4/5. So it's not looking particularly pretty, but we can actually neaten this up very nicely. We can, because we want to turn this 2/5 into a 1, and we just multiply by 5 over 2. So not changing our first row, not changing our second row, and our third row is going to be 2/5 times by 5/5, and here we've got 4/5 times 5 over 2, which is just 2. So things are looking pretty good. The only thing that remains for us to do is make sure that this 1 that's sitting in our bottom left part of our augmented matrix is the only non-zero thing in the column. So we need to make this 4 and this minus 3/5 into zeros. So what we're going to do is we're going to subtract various multiples of row 3 from row 2 and row 1 to do that. So let's start with row 1. So we're going to say row 1 minus 4 times row 3. And you'll notice that because row 3 has zeros there, it's not going to affect the 1 and the 0 that we carefully worked to get there. So we're going to have just writing down stuff that's not changing. Okay, so we've got 1 minus 0, which stays as 1, 0 minus 0, which is still 0, 4 minus 4, which is 0. Now we've got 5 minus 8, which is minus 3. So we're almost there. We just have one more entry to sort out over here. And again, we're going to add the appropriate multiple of row 3 to row 2 to sort that out. So here we've got row 2 plus 13 over 5 of row 3. So row 1 is not changing, row 3 is not changing, and now we go 0 plus 0, which is 0, 1 plus 0, which is 1, minus 13 fifths plus 13 fifths is 0, and now we've got minus 1 fifth plus 26 fifths, which is 25 fifths. 25 fifths is the same as 5. Phew, so that was quite a lot of work, but notice what this has given us. We can now take this augmented matrix and write straight out the equivalent linear system, which shows us exactly what the solution to the original system is, because our first row corresponds to the equation x1 plus 0x2 plus 0x3 is equal to minus 3. And if we ignore these terms, since they're 0, what this is telling us straight off is that x1 is equal to minus 3. Similarly, our second row of our augmented matrix says, well, we have 0 times x1 and x3, it's just x2 that we've got, and it's equal to 5. And our third row tells us that x3 is equal to 2. So we have taken a system where we couldn't read off the solution. We transformed it into an augmented matrix. We did a bunch of tedious but necessary transformations to that augmented matrix and got it into a system where we can read off the solution straight away. Now, I realize that this might seem cumbersome, but it turns out you'll get pretty quick at doing this, and it's a lot more straightforward than trying to solve 3 equations and 3 unknowns by an ad hoc method. Let's look at a few more examples. Now we know that there are 3 possible solution sets to a system of linear equations. We can have a unique solution, which is what we've got in this case over here. So the only values of x1, x2, and x3 that solve the system are these ones. You can also have infinitely many solutions, and you can have no solution. So it's instructive to work through examples that are going to show us what the augmented matrices look like for cases where you have infinitely many solutions or no solution. So here we go. We've got another system of linear equations. We've got 3 variables, 3 equations. So I've gone straight ahead and put this into an augmented matrix, and off we go. So we already have a 1 in our top left, so we don't need to do anything to that. Our next mission is we want to turn this 2 into a 0. So we're going to subtract off, well, you could pick your favorite row. I'm just going to use row 1 because it's just simple, but you could use row 3 instead. So we're going to say row 2 minus 2 row 1. Okay, so I'm not changing my first row. I'm not changing my third row. I'm changing my second row. So I've got 2 minus 2, which is 0, 1 minus minus 2, so that's 1 plus 2, which is 3, 1 minus 4, which is minus 3, and I've got 8 minus 2, which is 6. Good. All right. So now we need to tackle this one here, because we've got our leading one, so we need to have zeros in the rest of the column. So I'm just going to subtract row 1 from row 2. Row 3. So row 3 minus row 1. Okay, so I've got 1 minus 1, which gives me the 0 that I wanted. I've got 1 minus minus 1, which is 2. And I've got 0 minus 2, which is minus 2. And I've got 5 minus 1, which is 4. So I've finished with this first column over here. I've got my leading one and everything else is zeros. So the next thing I want to do is in my second row, second column, I want this to be a 1. So the simplest thing to do here is just to divide through by 3. So got 1 minus 1, 2, 1. I've got 0, 3 divided by 3 is 1, minus 3 divided by 3 is minus 1, 6 divided by 3 is 2, and I haven't done anything to my second row, my third row. So this was 1/3 row 2. So now I have my leading 1 in this row, so I need to have zeros above and below it. So you can pick how you want to work this. I'm going to work with this 2 first. So I'm going to say row 3 minus 2 row 2. So I'm not changing my first row. I'm not changing my second row. And in my third row I'm saying 0 minus 0, 2 minus 1 times 2, which is 2, minus 2 plus 2, which is 0. Sorry, messed up. So I was saying 2 minus 2, so that should also be a 0. And for this entry I've got a minus 2 plus 2, which is 0. And I've got a 4 minus 2, which is 0. So notice that we've got a row of all zeros. Well, we already knew that this could happen. Working with equations, we got 0 equals 0 sometimes, so that's fine. And we just want to check, is our row of zeros below everything else? Yes, it is. That's great. So now what we need to do is look at this column over here, because we still need to get zeros everywhere else in that column. So we need to attend to this minus 1 here. So the easiest way to do that is to say row 1 plus row 2. So we get 1 plus 0, which is 1, minus 1 plus 1, which is 0, 2 minus 1, which is 1, and 1 plus 2, which is 3. Nothing else has changed. So now we're left in a situation where ideally we would have liked to have had a 1 over here because that would give us a unique solution, but we don't. So what do we do?